Yeah. So, so in many realistic national security scenarios have the following properties. They have multiple agents, often it's more than two. They're not necessarily zero sum. They have repeated interactions, sequential actions, probabilistic events and transitions, and imperfect information. And so I'm aware there's been a lot of works that cover some subset of these complexities, but I'm not aware of any work for modeling and algorithms for national security scenarios that cover all of these. And so in this presentation, I'll be presenting a model and algorithm that covers all of these complexities. So to review, a stochastic game has a finite set of states or stage games, a finite set of players. Each player has a finite set of actions available. There's a transition function, and there's a reward function that's a function of the state and the actions. And sometimes there's a discount factor also. So challenges in these games. So first off, computing a Nash equilibrium in multiplayer games and two-player general sum games is PCAD hard. For stochastic games, if there's 3 or more players and there's no discount factor, it's actually an open problem whether a Nash equilibrium or uniform equilibrium exists. There's been some prior research on two-player stochastic game models for national security, which focus on computing Stackelberg or correlated equilibrium. And recently, I have a paper that was published at the Conference on Distributed AI that's on a 4-player naval strategic planning problem that's modeled as a stochastic game with perfect information that I'm going to be building on that model and approach. And so I'm going to roughly start by presenting that, that game model and that algorithm. So before I jump into that, the only work I'm aware of for multiplayer imperfect information stochastic games was actually work I did early on in my PhD applied to a 3-player poker tournament. Now that setting had a property that made it much simpler than the general problem. In that tournament, players were dealt a private hand, and then they play the hand out, and then they move to the next state, and then they basically forget the private hand they had previously, and they were dealt a new hand. And so the private information doesn't persist to other states. It's local only to the state you're in. And so this is a pretty significant limitation. And so I'm going to call this case local imperfect information, when the information doesn't extend beyond the current state. If the imperfect information extends throughout the game, either remaining the same or changing dynamically, I'm going to call that persistent imperfect information. And so, as I'll describe in a minute, the best existing algorithm for multiplayer stochastic games, either with perfect information or with local imperfect information, is called parallel PIFP, where PI stands for policy iteration, FP for fictitious play. And so this was demonstrated to converge quickly to provably close approximations of equilibrium in both the 3-player poker tournament and this 4-player naval problem. And but unfortunately, as I'll talk about, that algorithm can't be applied to persistent imperfect information. So roughly, the model we're going to be looking at is roughly motivated by this freedom of navigation problem, where in the South China Sea, where ships, blue ships and red ships are trying to navigate, and they may encounter each other and have some sort of an engagement. So this was the perfect information hostility game, has a set of players. So in our experiments, we're going to assume 1 blue player and 3 red players, 2 through 4. Each player has a set of actions. Some subset of the moves are counter moves of the others. And there's going to be a probability of a blue success and a red failure, given a move's defended against or undefended against. Similarly, a success for a direct red success and blue failure, and then some probability that there's no immediate success and the game's going to repeat. If there is an immediate success, there's a payoff, a terminal payoff for each player. And each move has a hostility level. And so if the game does repeat, it's going to repeat, but now the hostility is going to increase by the sum of the hostilities of the actions chosen. And so if the game hasn't ended and the hostility reaches this threshold K, then we enter what's called kinetic mode, and all the players are going to get this negative kinetic payoff, and the game is over. So this was the perfect information hostility game. We model it as a stochastic game where the state's Gn, where n is the sum of the hostility levels so far. And so we're going to have two additional terminal states, B and R, and GK is the terminal kinetic state. And so basically the game's either going to end or going to transition to a new state. And so in our experiments, we're going to have K equals 300, well, and also K equals 150, kinetic payoff negative 200, and the regular payoffs plus minus 100. So I'm not going to get too into all the details, but each player has between 7 and 9 actions. The hostilities are going to vary, like fire missile has very high hostility, bridge to bridge very low hostility. I created this game by talking to a military expert. Some of the actions are countered by the other players. And so the high level algorithm is going to be integrating game solving algorithm with the value update procedure. Now for game solving, we have a multiplayer 4-player game. And so we're going to use fictitious play. Another algorithm, regret minimization, has been successfully applied to multiplayer poker. I have a paper on archive. So for computing, approximating Nash equilibrium in multiplayer games, fictitious play actually performs better. And so we're going to use fictitious play. I also have a separate paper for if we wanted an exact equilibrium in multiplayer games. I have the fastest exact equilibrium as well. And so we're going to combine this game solving algorithm with the value update procedure. Once we've computed the strategies at all the states, assuming values for all the other states, we're then going to update the values either using policy or value iteration. And so I'm not going to get too into it. The original algorithms, both for value and policy iteration. And so once we've run the algorithm, right, it's not going to have any guarantee. Once we've run an algorithm, we can then check, well, how far from equilibrium is it? So given fixed strategies, assuming the other players follow the strategies, we can compute a best response by just a single agent MDP and compare that to the value of the policy. And so for the hostility game, we developed a parallel version of this, parallel PIFP, where we solve all of these stage games in parallel independently. And so I considered both variants of the value iteration and policy iteration. All of the versions of the value iteration failed to converge, and all the versions of policy iteration did converge. So this parallel PIFP has been shown to be the best, and so we're going to be building on that. And so to make this game imperfect information, we are going to assume each player has a private information that corresponds to its strength or amount of resources available. We're calling the type. Larger type is increased strength. We're going to assume, in our experiment, we're going to assume that it's just 1 or 2, and that initially it's uniformly random, and then of course it's the beliefs are going to change as the game continues. And so how does this affect the dynamics of the game? Well, basically, before, if the blue player would have won with probability P, now it's going to win with probability P to the TR divided by TB, where TR is the type of the red player, TB is the type of the blue player. And so basically, if you have a higher type, you're more likely to win in an encounter. So we could try to basically apply the previous algorithm to this setting. However, it's going to run into an issue. So basically here, we also need to worry, we can solve the games separately, and then we need to update the type distribution for all the states to make them consistent with the strategies we've just computed. And then we compute the values consistent with these types. And so this seems straightforward. However, it runs into a problem that when we're solving a given stage game, we're assuming that the players have types according to the strategies from the preceding iteration. However, in the games preceding this state, we're now computing new strategies. And so the types that they have when we're actually at this state might be different from the ones we're assuming we have. And so this is problematic. And so we can improve on this using the observation that in this particular game, the states form a directed acyclic graph where, because we can only transition to states that have a higher hostility level. And so this allows us to come up with a new algorithm. We're calling this ST-PIFP, where we solve the states sequentially, then we update the type distribution given the solution, the strategies we've just computed. and proceed according to a topological order. And now this unfortunately is sequential and it doesn't have the linear parallel speed up. I'm not going to get too into it. We can also have an improved version where, so for that algorithm, we assume there's a single value for every player and every state. And so in reality, the value depends on the state and the type distributions. And so we can simplify it to an extent. Do I have 3 minutes? Okay, thank you. We're going to assume that there's a separate value for each state and combination of types, not distribution, but combination. And so here, this makes it more complex algorithm. However, the bottleneck is still game solving. And so it doesn't increase the running time by that much. And so I'm not going to get into the code. One final thing I'll mention now, if we want to compute the epsilon, the exploitability, it's no longer an MDP with this imperfect information. It's a POMDP, which is p-space complete as opposed to polynomial time. And so we have an algorithm that essentially it recursively computes the optimal value for a given belief state by recursively calling itself for the updated states it could transition to with the horizon t-1. And so we do various implementation enhancements. We ignore very small transition probabilities. And so the experiments, we experimented first on using k equals 300. So we saw that using the type dependent values took about 23 minutes per iteration, and not using it took about 20. So it didn't increase the time that much. Now the checking algorithm didn't converge. It only converged for the first few iterations. The later iterations had a lot of randomization, and so it didn't. And so to check the algorithms, we ran them on a smaller game with k equals 150, where it did converge. And so we can see the exploitabilities for the type dependent value and the non-type dependent, which are approximately 5% and 1% of the smallest payoff magnitude. And two observations are that the higher type value produced the greater expected payoff, as you would expect. Another interesting observation is that the overall expected payoffs for all three of the red players were identical, yet they differed for each type. For example, we can see they're all 4.915 for the player 2, but for type 1, it was negative 24 and plus 33. Now for player 3, it was also 4.915, but for type 1, negative 10, type 2, 20. And so just to conclude, we presented new algorithms for multiplayer stochastic games with persistent imperfect information shown to compute epsilon equilibrium for small epsilon in this naval problem, new approach for evaluating strategies in this setting. And in the future, I'd like to improve the algorithm for the best response so we can compute the epsilon in larger games. I'd also like to compute an approach that generalizes to a broader class of games, not just this persistent imperfect information, ideally to all stochastic games. And so these approaches might involve more efficient parallelization. So that's it. Thank you.